minus 1/3. Are we all good on that? Okay. Next thing we have to do, who asked this question? We want to get V prime. You follow me? We need to get this voltage that would occur just as the switch closes. So what is that going to be? Well, remember, you just replace this whole business with 100 ohms, right? At t equals 0, it's only 100. So this is going to be actually, just write it down, it's going to be the source voltage times Z naught, bless you, over Z naught plus RS. That's the form of it. Do you agree, class? Everybody see this okay? All right, do the math on this one. What is it? Well, it's 5, right? Times Z naught is 100, right? And RS is 50, so that's over 150. So that's going to be 5 times 2/3 or 10/3 of a volt. Do you agree with that? You all follow me? Now, after that, regardless of where they want the voltage, you create that bounce diagram. That's it. All right. So if we create the bounce diagram, and try to draw this thing to scale as best as possible. You can keep going down as far as you want, but oh, you know what? We didn't get the initial time constant. This is going to be time on this axis. This is 0. This is going to be TL. I think he calls it TL, but I'm not sure. I call it T delay. This is 2T delay, 3T delay, and we could keep going if we need to, 4T delay, but it really doesn't matter at this point. Now, at T equals 0, V prime occurs here. We didn't actually get this. What is the time it takes TD for it to go one way down there? Class? I'm just calling this the time delay. I think in what we're supposed to say it's T sub L, but it doesn't matter what symbol you use. It's going to be the length of the line over the velocity on the line. Do you agree with that? What's the length of this line?
50 centimeters.
50 centimeters? All right, so it's 0.5 meters. And what's the velocity?
2.5 times 10 to the 8.
2.5 times 10 to the 8 meters per second. What's that going to be? It's nanoseconds. What? Is that right?
2 nanoseconds.
2?
2 nanoseconds.
All right, so we got 2 nanoseconds. That's TL. So this is 2 nanoseconds. This is 4. You all with me, class? Now draw the bounce diagram. Remember, this is the source. And this is the load. And you just do this. Dink, 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 dink. So this is going to be V prime. This is going to be gamma L VP prime. This is going to be gamma L gamma S VP prime. And we can put the numbers in. I'm just showing you the general form. And this is going to be gamma L squared VP, gamma L squared times gamma S VP prime. Are you all with me? Now again, that diagram will hold true for any kind of a pulse problem. Where it's strictly positive. You all with me, class? You just fill in the blanks. Now, where do you want the voltage at? You asked it, where do you want it at?
The load and the input.
All right, load, input. We'll start the load, okay? Everybody? Can you all see this in the back? Far corner. Can you guys see it? I'm always worried. I cannot see the board very well. When I have to sit at the very back of the room in the Senate meetings, if anybody's up here and they're just writing little things up here, it's worthless. I have to come down for it. Okay, so now we're going to do this, but we're doing it right here. Here's where we're going to start and go down. So let's do this. Here's time. I'll start this. This is T delay, which is going to be 2 nanoseconds, really. Here's 2T delay. Here's 4T delay. And we can keep going 5T delay. So what happens? Well, as I'm coming down here, it's at 0 volts. is the voltage at the load. It's going to be 0 volts until what, class?
2.
And what happens there? Now we have to simultaneously add the incoming and the outgoing pulse. Do you see that? So you have to add Vp prime plus Vp prime times gamma L. So it goes right up here to, you might as well just call it Vp prime times 1 plus gamma L. Now we've got the values down there for all these, so we just add the numbers correctly. Y'all with me? You're going to have a certain value. We'll fill them in a second. Is that, you with me so far? Keep going. How long is it going to stay there? Well, until what? Now, you got to go what? Not 2, but 3. Right? It's got to go back and forth. So over here, I put 4. I should have put 3. Make this 4. Now what happens over here? That was already there. Right? Now we add to it the incoming, this, and the outgoing simultaneously. See it back there? All right, so you have to add them both, and I don't know what the, does it go up or down? I'm not sure. I'll have it going down right here. But the value here is going to be that, Vp prime times 1 plus gamma L. Then you have to add this coming on, so it's plus gamma L, gamma S. And then you have to add what? Gamma L squared gamma S to that. Now, I don't know what that is, but that's the progression of things. Does that answer your question? I've got something I'm going to say about this in a second. But now, how many see this right here? Everybody? All right. Anybody not see it? It's pretty straightforward if you think about it. It's not hard to understand. It's just bouncing back and forth. Now let's do the voltage at the load, did you say? Or at the source? Source. Okay. So I'm going to do that over here. If you want to, we can put the numbers in, but I think you can do that part of the math fairly straightforward. It's just using the correct values. Now, for the source value, V source versus time, and call this what? TL, or T delay, 2T delay, 3T delay, 4T delay, it doesn't matter how many of these. So here, remember, you're starting right here, right? We're coming down instantly, it goes to Vp prime at T equals 0. So we go up to Vp prime, right? And whatever that is, 10/3, right, class? All right, it stays there for how long? So you hit this point. Y'all see that, class? At that point, you've got to add 2 components to what was already there. This and that, correct, class? Y'all with me? And so what's that going to do?
You have to add the VP prime at the top too?
It's there.
Oh wait, okay, you just add it.
It's there already. All right, it hasn't, there's nothing got rid of it. All right, so we keep going and we add, what happens? When we hit here, now it goes either up or down, and it goes to a value that's Vp prime, right? And now it's going to be 1 plus what?
Gamma L.
Gamma L plus what? Gamma L times gamma source, right? Because that's Vp prime times gamma L coming in this way. This is going to be leaving simultaneously. So you have to add that and that together to what was it. Y'all see this? How many see this? What's this asymptotically going to go to at either the load or the source as t goes to infinity? Class?
State.
Yeah. What's the value?
5.
Think of this. Forget the transmission line. As t goes to infinity, it ain't there. Right? Take the load and put it here. What's the load? An open circuit, right? What's the open circuit voltage going to be when that switch closes as t goes to infinity? Class?
5.
Just the source voltage. It's just going to be 5 volts. Do you agree with that, class? How many understand that? Now, there's one aspect of this problem I didn't cover in class on Friday, and I want you to be attentive here. I'm not going to ask this question on the quiz, but you need to know this. What if I wanted the current as a function of time? Now, here's the mistake. People will say, well, it's just the voltage here, which we got at the source, and they'll divide it by Z0. Do you understand me? That would be a mistake. All right, because the first pulse, it'll work. But what you really need to do is take the voltage here, which is 5 volts. Just follow this. If I want I of t, I would take the source voltage minus the voltage Vp, V source, which is a function of time, and you divide it by that source resistance, Rs. Now that will be the current. Do you all hear me on this? Now just think about this, right? It's the voltage across the resistor, this is always true, divided by the resistance is the current. Do you all follow me? How many see this? Now what happens? Instantly, right, we get a current. How much current do we get? Well, we get, what is this going to be? It's really going to be just like 5 volts minus 10/3, right, over Rs. That would be the current that flows. But then as the second pulse comes down, the voltage changes here, right? And you would have to take 5 minus that change divided by Rs. But hear me now. What happens as time goes to infinity? What's the voltage here? Minus 5 minus 5 is?
0.
How much current flows?
0.
Asymptotically goes to 0. Now, that's for an open circuit. If it was a resistance here, or a finite resistance, then as t goes to infinity, the current would just be this voltage, source voltage, over Rs plus RL. That transmission line would just look like a pair of wires. Do you all hear me? If it is a short circuit here, then the current as t goes to infinity would look like Vs divided by Rs. Yes?
What if you then short it to ground at the end?
What?
If you short, instead of having an open circuit at the end of the transmission line, it's shorted to ground.
Which end?
The end of the transmission line. At the,
I mean, which end, top or bottom?
if they're shorted together.
Here?
Yeah.
That's a short circuit. If you have a ground
Is there any
here,
voltage across there then?
there's no voltage across a short circuit. That's the definition of a short circuit, 0 volts.
Yeah.
I mean, it's a concept.
I'm just asking then, what would be the your current flow through there? Would it just be your
As t goes to infinity,
yeah.
at infinity, it would look like that short circuit appeared right here. Forget the switch. The short circuit, right? You would have just Vs over Rs would be the current to that one. Y'all hear me? That's all it is. It's not hard to see when you think about it. Okay? So I wanted to cover that point. Now, there's one other problem I didn't cover, the pulse. Was that 4/4? Okay. The pulse is interesting. The only thing you have to do is add a negative going waveform. In Whitworth's book, it was what? Was it 2.44? All right. Let me put this up here, because this is actually a very easy problem, but people get confused sometimes. And if I have time, I'll do the capacitor inductor terminations. We got this eraser. It's fantastic. All right, so this is 2.44, I think, in Whitworth's book. Now there he has this type of effect. He has a source, but it has a pulse like this. And he has a resistance, Rs, that we'll get to. And he has absolutely no switch. He doesn't need to, because this is going to have a pulse form. And I'll get to it in a second. Then he has a transmission line. And he has a load. And I don't remember what the load is on this one. We'll get to it. All right, so what's Z0 on this one? Help me out, you guys.
50.
50? Is that right? 50? Okay. What's this?
150,
150. What's this?
30,
Okay, what's the length?
point, oh,
10 centimeters.
10 centimeters. What's the velocity?
.666 C.
2/3 C. Okay. All right, now, just, here's the thing. For that pulse, he's going to do this. He's going to have something, it's going to have a duration of 0.4 nanoseconds, and it's got a value of 10, is it, Jeremiah? I forgot. For Whitmore's, the VS, what is it?
Yeah, 10 volts.
Is it 10? Yeah. Okay. So this is VS as a function of time. So here's what we do. First thing we do is get what we always need to get, and that's going to be reflection coefficient, the load class. What is that? 150 minus 50 over 150 plus 50, or 200, right? That's minus 1, or I'm sorry. It's going to be plus, it's 100 over 200, it's 1/2. Is that right, class? Over here, what is it? For gamma S of the source, it's 30 minus 50 over 30 plus 50. And gamma S for this is what? Minus 1/4, is that right? Yes. Minus 1/4. We've got that. All right, now tell me about the time delay. Well, the length over velocity is going to be what? Length is 10 centimeters, 0.1 meters, over 2 times 10 to the 8th. So that's 1/2 times 10. Let's see, that's going to be, is that 10 to the minus 9th, or 1/2 nanosecond? Is that right, class? Right? Or not? Okay, now, start by saying to yourself, what does this really look like? This is a, well, this right here looks like 2 pulses. It looks like one pulse that's 10 volts that starts at 0. And then add to that another pulse that's minus 10 volts, but it starts at what? At 0.4 nanoseconds, right? And if you add these two together, you get this waveform right here. You all follow me? How many see this? Far back, do you understand that? You're just saying this pulse right here is constructed from one waveform of 10 volts that starts at t equals 0, and add to it another waveform that starts at 0.4 nanoseconds, but it's negative. So when we do the bounce diagram for this one, I'm going to try to draw this a little bigger. And proportionality helps on this one. So here's 0. And here's going to be the first time constant, which was 0.5 nanoseconds. And then 1 nanosecond here. And then 1.5 nanoseconds. You can see the progression, what I'm trying to do here. If you have engineering paper, it'll help a lot in this one. Then after that, you start with the first waveform. Now, I didn't do this, but I think you know how to get V prime. So the only thing we're going to do is get the V prime for this 10 volt pulse. You with me? Everybody understand it? We're just going to get the bounce diagram for this pulse. So when I look at that, this V prime here will be simply equal to the source voltage, which is 10 times 50 over 80. So that's really just going to be 5/8 times 10. What is that? 6.25. Is that right or not? What is it?
6.25.
Y'all with me? So you start over here, and this is going to be the waveform of the first waveform. It's this guy. This is V prime. This is going to be V prime times gamma L. This is V prime, gamma L, gamma S, and so forth. Because waveform's going this way, this way, this way, and we can keep going, but I think you get the idea, right? I'm just doing what I did before for this waveform. You put in the value, 6.25. I don't know what that is, but you can keep on going, right? Key thing is that's positive, that's positive, that's positive. Maybe if I put a plus here, we get it. Now, let's talk about this negative going waveform. Same magnitude, opposite sign, right? But it starts at 0.4 nanoseconds. So it starts right here. That's negative though. It's going to have an exact same bounce diagram in terms of the actual directionality. So this is going to be V prime minus V prime. This is going to be minus V prime gamma L. And if we keep going, this is going to be minus V prime gamma L gamma source. But you all follow me, class? Take a good look, right? Now that's negative. So if we want the voltage waveform anywhere in the line, what do they want for that drop out of there? Middle or end or where?
They asked for all three.
All right, well I'm going to pick the middle because I'm not going to do all three of them. It's the same thing. If you come down here, this is time, and this is going to be, I'll call it V at L over 2. So it's right dead center in the middle. And now I'll try to draw this line so you see it. Here's the middle. I'm trying to go right down here, like so. You all follow me? That's the timeline I'm going down, trying to find the values. So take a look at this with, I think you get this. I start, it's at 0, right? It stays 0 until I go to half a time constant, or delay time, which is 1 nanosecond. Is it, class? So I keep going until I hit 1 nanosecond. And then what does it go to? Y'all see it? Just goes to V prime, right? Now that's a positive value. Y'all follow me? It stays there for how long? Until this hits, right? So that's going to be half a nanosecond plus a quarter nanosecond, or 0.9 nanoseconds, or I mean plus 0.4 nanoseconds, or 0.9 nanoseconds. Do y'all follow me, class? But it's a negative, right? So when you add this to that, you get zip. In other words, that pulse is sort of propagating down, and you can see effectively it goes to 0 at, it's actually, sorry, it's 1 plus 1.4 nanoseconds, right? Now, if you look at this, I came here, I hit here, right? Everybody with me on this? What happens next? Then a little bit later, yes, sir.
If it's half a nanosecond, wouldn't it be V prime at
Well, is the time delay? Sorry, it's a half nanosecond.
So it would be 0.25 nanoseconds.
I'm sorry. Yeah, I'm sorry about that. What I should have said, this starts at a half nanosecond. I'm very sorry about that. All right, and then if you add a half to a quarter, or to 0.4, right? This is 0.9 nanoseconds right here. All right, it's just the delay of the pulse, right?
What I'm trying to say is, if we're measuring it at L over 2, wouldn't it be 0.25 nanoseconds?
You are so right. I'm so sorry. It's going to be a quarter nanosecond right here, so it's 0.25 nanoseconds. Then add 0.4 to that. This would be 0.65 nanoseconds. I'm sorry about that. You're right. All right, now how long is it going to stay there? If you can follow the progression, go straight down until I hit this point, right? Well, where's that? Well, that's going to be at, is it 0.75 nanoseconds? Start the question. So at 0.75, what happens here? It goes what? Up again, right? But it goes up to what? Gamma L V prime. So it goes not as high. So here, it's going to be gamma L V prime right there. And how long is it going to stay there? You add 0.4 nanoseconds to that. You're with me, class? And then it goes to 0. So what is this? So that's going to be the progression of the pulse. You're picking a point, I mean, at pointing on the line and going, look at the bounce diagram, go right down the constant time, or I'm sorry, hold L over 2 constant, go down as time changes and just add the values. Are you with me, class? That's it. That's all you do on these pulses. Yes, sir.
Looks like the formula for like the blue line.
Say that again.
Are the blue lines or the like that one? I don't know what
The
to call
blue line would be the negative going one. I'm just
it.
trying to show.
Each one is always negative of the other one?
Well, in order for this to work, right, I've got a pulse that's only on for 0.4 nanoseconds, right? I'm going to say that's really the sum of one pulse or one waveform that's 10 volts, 10 U of t, plus, you could say, minus 10 U of t minus 0.4 nanoseconds. So I get the bounce diagram for this one and the bounce diagram for that one that's delayed by that. And I just pick any point and keep going down and just add up the values that I see. Some negative, some positive. That's it. Did that answer you?
I got that part, but how do you know which ones the blue ones are negative? Like, what can you write?
Well, this is negative. You could put a number here. I'm using blue to indicate that's minus B prime.
What's the, so the, I'm saying, it's minus B prime and the next one's B prime, gamma.
Well, the
L.
purple is plus, the blue is negative. So plus, negative, kills it, goes to 0. Plus, right, but this is B prime gamma L. Plus, then kills it right here, right?
Okay, that's also negative. I just couldn't-
Yeah. The blue is negative. What I'm trying to do is show you the wave, the bounce diagram for two pulses, one positive, one negative, same magnitude, but time delayed by 0.4 nanoseconds. Can you all follow me? How many understand this? All right. I'll give you more time on this quiz. So I'll get it. I'll get you going on this. And